Welcome to ePathshala, content for PG courses. So, we are looking at a series of content on computer networks. So, we have been taking a top down approach. So, we have started at the application layer and we moved down to the transport layer. We have been looking at the TCP protocol. So, at the TCP protocol, we have been looking at how TCP provides reliable data transfer. So, what we will be looking at in today's lecture would be the details of how TCP does its connection establishment, how the state diagram can be understood to understand how TCP does its connection establishment, and we will also take a look at how TCP does adaptive flow control. So, as we said, there are a number of techniques that are used by TCP for reliable transmission. First is the connection oriented mechanism, second is sequencing and acknowledgements, third is flow control, fourth is retransmission, and fifth is congestion control. So, we will take a look at details of connection oriented mechanism and flow control now. So, to give a quick overview of our connection setup and teardown, remember that we do a three-way handshake for the connection establishment process. So, we have a SYN, SYN plus ACK and an ACK. So, this combination is what is used for the connection establishment process, and similarly for the teardown we make use of these two flags, the FIN and the ACK. So, you have a FIN and an ACK in response to that which needs to be given in order to tear up the connection. But what we also have with respect to TCP is that there are multiple options that are available when you are doing an open. So, normally there are we look at two basic mechanisms. One is called as the passive open and the other is called as the active open mechanism. So, if you look at passive open, there are two options that we have. One is called as the unspecified passive open and a fully specified passive open. In unspecified passive open, we are waiting for a connection to come from any remote host or any remote port. So, this is what is normally done in the case of a web server and so on, because a server is waiting for a connection that can come from any host or any port. But you could also have a fully specified passive open, wherein you are waiting for a response or for a connection to come from a particular remote host and a port. Now, this is not used very often, but it is the unspecified passive open that is used most of the time. But TCP does have this option of doing both unspecified as well as a fully specified passive open. There are some cases in embedded systems where the fully specified passive open is used. Okay. The other option that we have is the active open. So, in the case of an active open, when you open up a TCP connection, you specify all the four different parameters that are required for a connection. That is, you specify the remote host and the port number, and of course, you also know the source host and the port number. So, all the four parameters are available. So, this is an active open. So, you are telling TCP, you are instructing TCP that it has to connect to a particular host and at a particular port number. Okay. So, with this passive open and an active open approach that we have, we will look at how typically a connection is established between a server and a client. So, normally as I said, a server would be a one which makes a passive open, and if you look at that, initially it would be in a closed state, and once it makes a passive open, will move into what is called as a listen state. The client on the other hand will make an active open, and when it does an active open will send a SYN. If you look at the state diagram, we have states, we have transitions, and on the arc which denotes a transition, we normally specify the event which is causing it to happen and an action that is taken in response to that. So, the event that we have is an active open which comes from the application, and in response to that TCP will send a SYN to the other side. So, you can see that the SYN is indicated over here, and now it will move into what is called as a SYN send state. Similarly, now on the other side, the server which is the listen state will receive the SYN, and in response to that go to a SYN received state. Okay, and once it does that, it will send an ACK, and once it sends an acknowledgement, then automatically it will go to the established state. So, this is what you will see. So, let us look at this in detail. Okay, so, this is just the connection establishment process alone that is kind of zoomed up. So, as we said, you need to have this process, right? You need to have a SYN, SYN plus ACK and an ACK. So, this is the three-way handshake that we want. So, look at what is happening here. So, your server has started with a passive open, is the listen state. The client makes an active open, has sent a SYN, has come to the SYN send state, it is waiting for a SYN plus ACK to come. Now, the server which is in the listen state has received a SYN, right, from the other side, and in response has sent a SYN plus ACK and goes to the SYN received state. So, in the SYN received state, so we are right now over here. So, A right now is in the SYN received state, SYN plus ACK. Now, once it is received, B is in the SYN received, sorry, A has sent the SYN which is the client, and B is the server. So, B is right now in the SYN received state. Now, it is waiting for an ACK to come. So, when A receives the SYN plus ACK in the SYN send state, it will send out an ACK. which you can see over here on this arc. SYN plus ACK is received, that is the action which causes this particular, that is the event which causes an action of ACK to be sent. So, once that is done, this will move into the established state. Once this ACK is sent, you can see that this fellow who was waiting so far in SYN received state will receive this ACK, and on receiving this ACK, he will also move into the established state. So, at the end of this process, both the sides would have moved into the established state, and then they can start transferring data. So, this is the connection establishment process. So, similarly, if you look at the connection termination process, so this is the lower half of that state diagram, that big state diagram that we had looked at. So, you can see that there are again multiple states over here. So, we will take a look at these three different mechanisms that we have for tearing down a connection. So, one is that you have first one side closing the connection with the fin, for which the other side will respond with an ACK, and then you will have the other side sending a fin, and then its ACK being sent from A. So, if you have this kind of a four-way handshake that is taking place for tearing down a connection, look at what will be the different states through which the TCP connections will go through. So, we will start off with the established state. Now, one side's application asks us to close the connection, right. So, A for instance is asking it to close the connection. So, in response to its close, it will send out a fin, okay, and move into what is called as a fin wait state. So, basically what we mean by a fin wait state is that it is waiting for a fin from the other side. It has closed its side of the connection, but it is waiting for a fin to come from the other side. So, it waits in the fin wait state. It has sent a fin, right. So, on the other side, which is in the established state now, is receiving a fin, right. In response to the fin, what is it expected to do? It is expected to send an ACK. So, it sends out an ACK and goes into a state which is called as a close wait state. So, in this state, it is waiting for its application to close the process. So, when that happens, it will send out a fin. Okay. So, right now at this particular point, okay, one is in fin wait 1 state, the other is in the close wait state. Now, in the fin wait 1 state, what it receives now is it receives an ACK which has come from the other side. So, this is the ACK that it has received. Once it has received the ACK, it goes into another state called the fin wait 2 state. It is a second fin wait state, okay, because it is still waiting for the fin that has to come from the other side. Okay. Now, when will the fin come from the other side? That will happen only when the other side closes the connection. Now, the other side is waiting in this, B is waiting in the close wait state, and when its application sends a close as asking it to close the connection, at that time it will respond by sending out a fin and move into what is called as a last ACK state, where it is waiting for an ACK to come for the fin that it has sent. Okay. Now, look at what happens here. Now, this is sent out a fin. So, our A, which is waiting in the fin wait 2 states, receives the fin. On receiving the fin, it sends out an ACK in response to that, which is what is expected to do, and moves into what is called as a timed wait state. So, in the timed wait state, this is a temporary state in which it waits for about 2 lifetimes, that is the lifetime of a maximum sized segment, or whatever is the maximum time for which you expect an IP packet to be there in the network. Okay. So, you wait for some amount of time and then you move to a closed state, which means that you have closed the connection. Now, see that in response to the fin, we already sent an ACK. So, now this ACK would be received by B, so which was in the last ACK state, and on receiving the ACK, it will move to the closed state. So, you can see that both the sides would have moved to a closed state, okay, and both would have terminated their connection. Okay. So, one takes this path, the other one takes the path on this side. Okay. So, this is what happens when you have this kind of a handshake mechanism. Now, another possibility that we have is that you have the two fins crossing each other, that is both sides have indicated that they want to close the connection. It could happen, right. Both applications could have simultaneously informed their respective TCPs that they want to terminate the connection, in which case what would happen? Both would have sent a fin, right. That is, both of them will be in the established state and both their applications are sending them a close, in response to which they will send out a fin. So, this is the second scenario for tearing down a connection, where we have both sides giving a close simultaneously, in response to which both the TCP sides will send out a fin. Okay. So, this is what we have. So, both of them are in an established state, and from there both of them will send a close, will on receiving the close will send out a fin and move into the fin wait 1 state. So, you can see that the two lines here are basically indicating that both sides are following the same state transition. So, they are both waiting in the fin wait 1 state, and what happens when it is waiting the fin wait 1 state, what it receives is it receives a fin from the other side. It has sent out its side of the fin and it now receives its fin, the fin from the other side. The same thing happens at side B as well. So, when it receives this fin from the other side, in response to the fin, it has to send out an ACK. So, which is what it does. In response to the fin, both of them will send out an ACK and move into a closing state. Now, they wait in this closing state until they receive the ACK from the other side, and on receiving the ACK from the other side, they again go into a timed wait state, where they will wait for about 2 maximum segment lifetimes before they actually close the connection. Now, this 2 MSL timeout basically is done so that in case there are any delayed packets that are yet to be received, those will be received before the connection is closed. Otherwise, it could happen that when you have, if there is another connection that is opened with the same port number and same between the same IP addresses, there could be a problem of an old packet coming into a new connection and so on. So, to avoid that, this kind of a mechanism of a timed wait mechanism is used. So, this is the second scenario. The third scenario that you would have would be something like this, right. You have a fin sent from one side, and in response to that you have both a fin plus an ACK coming from the other side. Now, this fin plus ACK coming from the other side will happen if you are in the established state and your side, that is your process, is asking you to close the connection. So, which means you want to send out a fin, plus you have also received the fin from the other side for which you want to send out an ACK. So, this combination of B sending fin plus ACK is normally not shown in the state transition diagram, but you can see that it is a transition that will happen from the established state to the closing state. So, you would actually have a state which comes from here to here. Okay. So, that is normally not shown in the diagram, but this is a case that could happen. So, if that were to happen, so side B's TCP would come from the established state to the closing state after having sent a fin plus ACK. Now, A on the other hand would have been in the fin wait 1 state because it received a close and sent out a fin, and when it is in this particular state, what it receives is it will receive a fin plus ACK. On receiving a fin plus ACK, it will send out an ACK and move into the timed wait state. Now, since this ACK has been sent, the other side B, which is waiting in the closing state, will receive this ACK, and on receiving the ACK again move to the time wait state, and after the 2 MSL timeout will go and close the connection. So, you will see that this is the process that is used for closing the connection, and these are the details of the different states in which TCP will move before it actually closes the connection in all these 3 scenarios. So, next we will look at TCP's flow control mechanism. So, we have already looked at the connection establishment part. So, now we will take a look at the flow control mechanism. So, if you look at flow control, we know that flow control is something that takes care of the fast sender slow receiver problem. Now, when we talk of the slow receiver here, it could be that the process itself, that is the receiving process itself could be slow in terms of reading the data, or it could be because the buffer size is small, which also could limit the receiver's capacity in terms of receiving the data. So, how is it that TCP takes care of this flow control mechanism? So, that is what we will look at now. What TCP does is basically that it basically uses a sliding window approach, and it uses what is called as an adaptive flow control mechanism. Now, we will see where this adaptivity comes from. Okay. So, this adaptivity basically comes from the fact that the receiver constantly determines and advertises the amount of data that the sender can actually send. That is, it keeps sending out a window size, but this window size, which is normally specified in number of bytes, can vary. And based on this on the window size that it advertises, the sender side will send the required number of bytes into the network, and accordingly the receiver buffer will also receive it and keep sending out this, keep giving its feedback to the sender side. So, let us look at the different buffers and the different mechanisms that are used in TCP to do this. So, if you look at the header fields that you have in TCP, you will see that there are 3 fields here which are used for flow control. One is the sequence number, second is the acknowledgement number, and the third is the advertised window field. Okay. So, these are the 3 fields which are used for by TCP for doing this adaptive flow control, and we will see how these numbers are actually used. Okay. So, to determine the window size, what TCP does is that it will calculate what should be the actual advertised window size, right. So, I mean the receiver side will calculate the advertised window size and send it to the sender, and the sender on its part will calculate the amount of data that it can actually send based on this advertised window size. So, let us say for instance, this is your sender side buffer. Okay. So, let us assume that we have transmitted so many bytes, last byte sent, and this is the last byte that has been acknowledged. The blue color, let us say tells us the amount of data that is available in the buffer to be sent. So, out of this I have already sent so many bytes, up to this has been acknowledged, right, and now from here to here is the amount of data that is yet to be sent. So, now when I get my receiver's advertised window size, if the window size tells me that this much of data can actually be sent, out of which I have already sent so much, it effectively means that my effective window size is only so much, that is I can only send so much of data, right. That is the receiver advertised window size minus this amount of data that has already been sent is the additional amount of data that can be sent. Now, if the receiver receives more, as you send more data, the receiver receives that data, if it is sitting in its buffer and it has not been read by its receiver side application, then it will keep on reducing this window size. So, this is what you will see as a sliding window mechanism, where the window size can shrink or increase depending on how much of buffer capacity is available on the receiver side. Okay. So, this is typically what we have in terms of TCP in order to maintain this buffer on both sides. So, if you look at the sending side application, there are these 3 pointers which are used for buffer management. Okay. So, you have data being written by an application into the buffer. So, that we will call as the last byte written, okay, the last byte that has been written by the application. And TCP on its side keeps track of 2 other pointers. One is the last byte that is sent and the other is the last byte that is acknowledged. On the receiving side, similarly, the receiving side application is going to read data. So, we keep track of the last byte that was read by the application, and on the other side it is receiving data from the other side's TCP. So, we keep track of the last byte that was received and the next byte which is expected. Now, note that normally you would expect the next byte expected to be something which is greater than the last byte received, but that need not be so, because in TCP you can also receive packets out of order, but TCP will take care of ordering them and giving it to the application. So, this next byte expected normally is to indicate the number of bytes that have been received in order. So, up to this has been received in order. So, the next byte that is waiting for is this particular byte, which is exactly after this. So, there is some unreceived number of bytes that are there in this buffer. Okay. Some other bytes, additional bytes have been received after this, but it is not in order. Since it is not in order, this is the last byte received, but this will be the next byte expected. Okay. So, with these 3 pointers on the sending side and 3 pointers on the receiving side, TCP does its buffer management. Now, you can see that based on these buffers that you have, there are certain rules that should definitely be followed. For instance, your last byte act will always be less than the last byte sent, okay, less than or equal to the last byte sent. Similarly, the last byte that is sent will always be less than the last byte written. Obviously, you cannot send more data than what has been written by the application, right. So, that is what it means. And the number of bytes that you have between your last byte act and the last byte written by the application, this much amount of data will have to be held in the buffer on the sending side. Similarly, if you look at the other calculation of the advertised window size and the effective window size. So, if you look at the advertised window size, so you can see that the last byte sent minus the last byte act, the last byte sent is here and the last byte act is here. Last byte sent minus last byte act will be less than or equal to the advertised window, and your effective window that you have will be advertised window minus this amount of data that has been sent. Whatever be the advertised window value, that minus the amount of data that has already been sent but has not been acknowledged. So, which is last byte sent minus last byte act. This amount of data will be the effective window, that is the amount of data that you can now send. Okay. So, this is the effective window calculation. Now, we also have to remember that last byte written minus last byte act is the amount of data that is buffered by the application. So, which means that your maximum buffer size will have to be at least as great as that. That is, if your maximum send buffer should be greater than or equal to last byte written minus last byte act. Okay. This is so, we need to keep in mind that there is always a maximum, that is a finite size for the buffer. So, this maximum send buffer size is what will determine the total amount of data that can be buffered on this side. Okay. Now, if you let us say for instance your buffer is full, okay, or the buffer is almost full and the sending application is also trying to write some more data. Okay. So, if the amount of data that should be written by the sender cannot be accommodated into your buffer, then obviously you have to block the sender. You should not allow it to write the data into your buffer. Okay. So, that is also something that we do, that is you will block the sender if the last byte written minus last byte act, which is the amount of data that is still there in your buffer, right, the not yet sent, this value plus y, which is the number of bytes that you are now trying to write into the buffer. If this value becomes greater than the maximum send buffer size, then obviously you cannot write. So, you will have to block the sender. Okay. So, these are the various rules that are followed on the sending side to manage the buffer. Similarly, if we come to the receiving side, on the receiver side, you will see that there are again two simple equations or inequalities that we need to adhere to. The last byte read will have to be less than the next byte expected. Obviously, you cannot read more than what has come in order. Okay. So, that is the first rule that we need to follow, and your next byte expected will be less than or equal to the last byte received plus 1. Okay. It will be equal to last byte received plus 1 if all the bytes you have received are in order. Okay. Otherwise, it will be less than the last byte received plus 1. Okay. That is how it will be. Okay. Now, in addition to that, on the receiving side, let us look at the bytes that we need to buffer. Now, all the buffers that have been received, okay, and which have not yet been read by the application will have to be buffered. Okay. That is, all the bytes between your last byte read and the last byte received, all these have to be held in your buffer. So, which means your buffer size will have to be at least as big as this, or this value determines the number or your maximum receive buffer and this value here, they are related. That is, your last byte received minus last byte address, the amount of bytes, number of bytes that you need to actually buffer should be less than or equal to the maximum receive buffer size. This is the first condition that we need to look at. Second thing is the calculation of the advertised window. Remember that this is what is determining the entire flow control mechanism, right. So, how do I calculate the advertised window size? This window size is dependent on how much of actual buffer capacity is available for me at a particular point of time. That is, when I have received some data and the data is coming and sitting in this buffer, how much of additional space is there which I can indicate to the sender side. Okay. This is what we specify here as the advertised window. So, if you look at the advertised window, it is calculated as the maximum receive buffer size minus the next byte expected minus last byte read. Okay. That is, you can see that this is the total, let us say this is the total buffer size. Okay. So, so much of data is already written. So, how much more data can be received? It is whatever data can be fitted into this region plus the amount of data that can be fitted into this region. So, that is what we say by, that is what we get by saying this, advertised window is equal to maximum receive buffer size minus the next byte expected. So, which will be this region minus the last byte expected, right. So, which will be this region. So, this minus this. So, whatever you have in between these regions, leave out that, and whatever additional free space is there, that free space is what can be now given as the advertised window size. And as more and more bytes start coming in and filling in the buffer, if there are no bytes which are read by the application, obviously this advertised window value will start reducing. So, that is what we mean by shrinking the window size. Okay. But if the receiving application starts reading those bytes, then it will expand, and once it starts expanding, we say that the window size is expanded and more data can be sent. Okay. So, we will just take a quick example to understand how this actually would work. So, assume that I have a 2500 byte send buffer and a 2000 byte receive buffer. Okay. Let me assume that the maximum segment size is 500 bytes. Normally, we have something called a maximum segment size that is allowed by TCP to send to the other side. So, we will come to how this MS is determined later, but right now assume that the maximum segment size can be 500 bytes. Okay. So, look at what we have. So, initially 2500 bytes is send buffer, 2000 byte is the receive buffer. So, initially when the a SYN and a SYN plus ACK is sent, okay, I will first send out a SYN packet, in response to which I will get a SYN plus ACK from the other side. Now, when I send the SYN plus ACK, I will also receive the advertised window. So, the advertised window here, right, the advertised window here will be 2000 bytes, because the entire 2000 bytes that you have is available, is free for the on the receiver side. So, now up to 2000 bytes can be sent from here. But now, since we said that the maximum segment size is 500 bytes, assuming that your send buffer 2500 bytes have been written by the application, okay, and your buffer is full. Okay, now what you do is you will first send out the 500 bytes. Okay. Now, 500 bytes will be sent from the sender to the receiver. Once this 500 bytes is received on the other side, now look at this. Now, you have your 2000 byte buffer, out of which 500 bytes now will be filled by this 500 bytes that are coming from this side. So, now what will be the size of the window? So, out of your 2000, 500 is gone. So, only 1500 will be the window size. So, your advertised window size that you specify now in this packet will now be equal to 1500. So, on this side now, your 1500 will be this, and you will also be acknowledging the data that has been sent. So, your ACK will also specify, assuming that for simplicity we will start with the initial sequence number of 0. So, which means 0 to 499 has been received. So, 500 will be my next byte expected. So, 500 will be the ACK that is sent. So, here I have sent 0 to 500 has been sent, right, and now 500 has been ACKed. So, once this 500 is ACKed, this part becomes free again, and there is data now between 500 to 2500 that needs to be sent. So, now what I will do is, since I have already had an advertised window size of 2000, I can send more than one MSS of data, which means I would have sent this 500 bytes of data. I could also have sent another 500 bytes of data, right, and another 500 bytes of data. Okay. So, all these can actually be sent back to back. So, because up to 2000 was my window size, but when I, so up to 2000 bytes could have been sent, right. So, this is the amount of data that would be sent. So, 500, 500, 500, another 500. So, altogether 2000 bytes of data have been sent here. But when you receive the ACKs, you will see that this and sent on the other side, you will see that this buffer keeps getting filled slowly, and once all your 2000 bytes have been received, right. So, you will keep sending back an acknowledgement. But let us assume that by the time this 2000 bytes is received on this side, the receiver process reads some data from here. So, once it reads some data, this part will become empty. So, now what will happen, by the time it receives this 500 byte of data, it will send back an acknowledgement, okay, acknowledging all the 2000 bytes that have been sent, and it will also free up space for, since there is space available for another 500 bytes, will now again give an advertised window size and say that another 500 bytes can be sent. Now, since up to this has already been acknowledged and there is another 200 bytes, 500 bytes that is not yet acknowledged, this now can be sent. So, you can see that as the data is sent from this side to the other side and the receiving process is reading this data, as the data is read, there will be some free space that becomes available on the receiver side, and this will keep opening up the window. And on this side, based on the window size that is advertised from that side, you will send a reduced amount of data if you do not have enough of window size, but otherwise you will keep sending whatever window size of data that can be sent. Okay. So, you can see that effectively by using this mechanism, we get a very very tight management of the data that can be transferred. Okay. So, this is basically how the flow control works. Now, there are some problems that this flow control mechanism could actually get into. Okay. So, one of these problems is referred to as the silly window syndrome. Now, look at this scenario that we had just talked about. So, we said that 2500 bytes can be sent from the sender side, but the receiver has only a 2000 byte buffer. So, let us say for instance, even after this entire 2000 bytes was sent, the receiver side application had not read any data at all. So, what will happen then? Your entire 2000 bytes has come and filled the buffer, and there is no more place for any more data. So, what will be the size of the window that is advertised now? The advertised window size will become 0, right. So, if the sender is aggressively sending data and the receiver is not reading it at all, your advertised window size could become 0. So, what will happen is that because the advertised window size has now become 0, the sender will not be able to send any more data. So, what will the sender do? It will normally wait and it will send a probe segment. Okay. A probe segment is basically a 1 byte data segment which is sent to the other side, which is kind of sent in order to just probe to find out whether an additional amount of data can be sent or not. Okay. So, typically what we expect is that when the probe segment is sent, hopefully by that time the receiver would have read some data and it would have freed the buffer. So, then the receiver may open up the window so that the sender can start sending the data. But suppose the receiver is very slow, okay, and it has just read, let us say, only 1 byte of data. So, which means there is space only for 1 byte of data. So, your probe segment has 1 byte of data which goes and sits in that 1 byte of free space, and again your window size will be 0. So, what will happen when you do this is that the sender will end up sending small segments of data. Okay. So, it actually becomes almost like a stop and wait where you are only sending 1 byte segments. So, you are sending 1 byte of segment probe data, it will give you back an advertised window size of 0, again you will send 1 byte of data, again it will send you a advertised window size of 0 and so on. So, you will end up sending 1 byte packets to the other side. So, obviously, this is not what we expect with respect to TCP, because we are expecting efficient use of the bandwidth. Now, here obviously, if for 1 byte of data you are sending 20 bytes of header, it is obviously a waste of bandwidth. Now, there is another situation also when you can have this kind of a silly window syndrome, which is caused by the sender side itself, that is the sender itself is sending small packets. So, this is also a situation that we would like to avoid, because this will also, both these cases, whether it is caused by the sender or the receiver, when you end up sending small packets on the network, there is a whole lot of bandwidth that is consumed. So, to avoid this, there are some solutions that have been proposed. One of the things that we have from the receiver side is that once it is advertised a 0 window size, it can wait for some time before it advertises the next window size. That is, do not go on giving 0 window size advertisement, but delay your acknowledgements and give the acknowledgement only when you have space equal to at least a maximum segment size. Okay. This is one thing which can be done on the receiver side. Other solutions on the sender side similarly are that you can delay sending the data or avoid sending small amounts of data. So, one of the solutions from the sender side that we have for this is called as the Nagle's algorithm, which also avoids the tries to reduce the overhead that you have. Okay. So, what do we do in this case? So, basically what we are trying to understand here is how long should the sender delay sending the data. If it waits for too long, then it will hurt interactive applications which require small amounts of data to be sent back and forth. If it is too short, it obviously ends up with poor network utilization. So, the strategy that we use is either you can go for a timer based strategy or a self clocking strategy. So, Nagle's algorithm uses a self clocking mechanism. So, we will just quickly see what it does. This is what Nagle's algorithm is. Okay. So, what it says is when an application generates additional data, if that data that is generated fills a maximum segment, that is it is greater than one maximum segment size of data and you have enough window size, just send that data. Otherwise, if there is some unnagged data in transit, that is you have sent some data for which you have not yet received an acknowledgement, you buffer the data, that small amount of data that you have until that ACK arrives, okay? And only when that ACK arrives you will send the data, okay? Otherwise you will send it, that is if there is no unnagged data and there is only a small amount of data that needs to be sent, you will send it. Okay. This way Nagle's algorithm tries to reduce the amount of small packets that are sent. So, again a very quick example to look at how that is done. So, let us say the sender side is generating data at a rate of 100 bytes per second, okay, and assume that you have a maximum segment size of 250, okay, and the round trip time is 3.5 seconds. So, let us look at what will happen in this case. So, at time t equal to 0, let us say I am sending 1 MSS of data, okay. So, 100 bytes of data is generated. So, once 100 bytes of data is generated, okay, let me assume that since there is no data in transmit, even though it is less than 250, I will send my 100 bytes of data to the other side, okay. Now, at t equal to 1, another 100 bytes of data will be generated, okay. At this time, at t equal to 1, when this 100 bytes of data is generated, it is still less than 1 MSS. So, I will see whether there is some unacknowledged data in flight. Yes, there is some unacknowledged data in flight because I have sent this data for which I have not yet received an acknowledgement. When will I get the acknowledgement for this? It will come only after 3.5 seconds. So, only at t equal to 3.5 I will get this acknowledgement. Meanwhile, at t equal to 1 I have got 100 bytes of data, I will store this, I will not send the data. At t equal to 2, another 100 bytes will be generated. So, I will have 200 bytes of data in my buffer, I will store that as well. I will not send it because I still have this unacknowledged data. At t equal to 3 again, there will now be 300 bytes of data. The moment I have 300 bytes of data, it is greater than 1 MSS. So, I will go ahead and send 1 MSS of data, which is 250. So, now what I will have is I will have another 50 bytes of data left, which can be sent when at 3.5 when I get this acknowledgement. Okay. So, you can see that though I could have sent small 100 bytes of data, I did not send it because I was waiting for this acknowledgement to come and trigger my next transition, or I was waiting until the amount of data that accumulates becomes at least equal to 1 MSS of data. Okay. So, you can see that by doing this, Nagle's algorithm tries to reduce the number of small packets that are sent. So, this is the idea that is used here. So, to summarize, there are two things that we have looked at in this lecture. One is the connection establishment and termination, the state diagram details of that. And the second thing we have looked at is the flow control mechanism, how buffer is managed, how the advertised window and the effective window sizes are calculated, and how the silly window syndrome is handled using the Nagle's algorithm. Thank you.